Well, let me tell you something that sounds like it should not be true, but is. Every conservation law in physics, every single one, comes from a symmetry. Energy is conserved because the laws of physics do not change over time. Momentum is conserved because the laws do not change from place to place. Angular momentum is conserved because the laws are the same in every direction. This is not coincidence. This is not some happy accident. This is a mathematical theorem proven in 1915 by a woman named Emmy Noether. And it is probably the single most powerful result in all of theoretical physics. You see, symmetry dictates conservation, and conservation shapes reality. If you want to understand why energy cannot be created or destroyed, you have to understand symmetry. If you want to understand why the universe has structure, has forces, has particles, you have to understand symmetry. The whole thing, the Standard Model, quantum field theory, general relativity, all of it is built on symmetry principles. But here is where it gets strange. The universe we inhabit is fundamentally asymmetric. Matter exists without corresponding antimatter. Time flows forward, not backward. Forces that should be identical have wildly different strengths. Symmetry explains everything. Yet symmetry breaking creates everything interesting. Think about that for a second. Now, let me tell you the story of how we figured this out. In 1915, there was a mathematician named Emmy Noether, very brilliant woman. She was working on a problem in general relativity, Einstein's brand new theory, and she discovered something that nobody expected. She proved that for every continuous symmetry of a physical system, there corresponds a conserved quantity. If the laws of physics do not change as time passes, energy is conserved. If they do not change as you move through space, momentum is conserved. If they are the same in every direction, angular momentum is conserved. This theorem, Noether's theorem, unified conservation laws that had seemed completely unrelated. People had known about conservation of energy since the 1800s. They had known about conservation of momentum, but nobody understood why these laws existed. Why is energy conserved? Why does momentum never just disappear? Noether showed that these were not separate laws. They were consequences of space-time symmetry. The structure of space and time itself demands these conservation laws. And you know what? Noether received almost no recognition during her lifetime. She was a woman in early 20th century academia. Universities would not hire her. She worked without pay. She lectured under other professors' names because she was not allowed to teach officially. Hilbert and Einstein recognized her genius. Einstein called her work penetrating mathematical thinking, but the institutions did not. Today, every physicist learns Noether's theorem. It is foundational to particle physics, general relativity, quantum field theory. But in her own time, she was invisible. That is how physics is sometimes. Now, here is where symmetry becomes even more interesting. You see, the Standard Model of particle physics, the theory that describes every particle and force we have ever detected, is built entirely on symmetry, not the symmetry of shapes or patterns. Gauge symmetry, this is something deeper. Let me tell you what this means. Electromagnetism comes from something called U1 gauge symmetry. The weak nuclear force comes from SU2 gauge symmetry. The strong nuclear force comes from SU3 gauge symmetry. These are not just descriptions of the forces. The symmetries generate the forces. You can derive Maxwell's equations, all of electromagnetism, purely from requiring U1 gauge invariance. The photon exists because of symmetry. The 8 gluons that carry the strong force exist because of symmetry. The W and Z bosons that carry the weak force exist because of symmetry. Particles are not fundamental. Symmetries are. Forces are the consequence of demanding that the laws of physics look the same under certain abstract transformations. Now this sounds very mathematical, and it is. But let me show you what it means. Think about electromagnetism. An electron has electric charge. That charge creates an electric field. Other charged particles respond to that field. We call this electromagnetism. But why does this force exist at all? Why do charged particles affect each other? The answer is gauge symmetry. The laws of quantum mechanics have a kind of freedom. You can change the phase of the electron's wave function at every point in space, and the physics should not change. That is a symmetry. But if you just change the phase arbitrarily everywhere, you break the laws of physics. To preserve the symmetry, you need something that adjusts as you change the phase. That something is the electromagnetic field. The photon is the price you pay for gauge symmetry. The force exists because the symmetry demands it. This is why physics focuses so heavily on group theory and abstract mathematics. The math is not decoration. The math is the structure of reality. When physicists say the universe is made of mathematics, this is what they mean. The symmetries, these abstract mathematical structures, are more fundamental than the particles themselves. And you know what? This works. It works beautifully. Quantum electrodynamics, the theory of how electrons and photons interact, is the most precisely tested theory in all of science. Predictions and experiments agree to better than one part in a billion. The electron's magnetic moment has been measured to 12 decimal places, and theory matches experiment perfectly. The symmetry principle is not philosophy, it is how reality actually works. But there was a problem. If symmetry explains everything, why is not the universe perfectly symmetric? Why is there matter but almost no antimatter? The Big Bang should have created equal amounts. They should have annihilated completely, leaving only radiation. Yet we exist. Every atom in your body is matter. The stars are matter. The galaxies are matter. Antimatter is almost nowhere to be found. Something broke the symmetry. And why do electromagnetic and weak forces have such vastly different strengths? Electromagnetism reaches across the room. Your body is held together by electromagnetic forces, but the weak nuclear force has a range of about 10 to the minus 18 meters. You need a particle accelerator to see it. Yet at high energies, these forces are unified. They come from the same symmetry. Something broke them apart. The answer is spontaneous symmetry breaking. And this is one of the most beautiful ideas in all of physics. Here is how it works. The laws are symmetric, but the state of the universe is not. Let me give you an analogy. Imagine a pencil balanced perfectly on its point. The laws governing the pencil are rotationally symmetric. There is no preferred direction. North, south, east, west. The physics is identical in every direction. But the pencil is unstable. It is going to fall. And when it falls, it picks a direction. That direction is random, could be any direction. But once it falls, rotational symmetry is broken. The outcome is not symmetric even though the laws are. In particle physics, the Higgs field does exactly this. The Higgs field permeates all of space with a non-zero value. That value breaks electroweak symmetry. Above a critical energy around 100 billion electron volts, the electroweak scale symmetry is restored. Electromagnetic and weak forces become indistinguishable. They are two aspects of the same force. Below that energy, symmetry breaks. The forces split. Particles gain mass. The universe cooled below the critical temperature, a tiny fraction of a second after the Big Bang. Symmetry broke. The Higgs field settled into its current value, and that is the universe we inhabit. The broken state. Now, here is something important. The Higgs mechanism is not speculation. In 2012, physicists at CERN detected the Higgs boson. This is the particle associated with the Higgs field, the quantum ripple of that field. Its mass is about 125 billion electron volts, exactly where the theory predicted it should be. The symmetry breaking is real. We have measured it. But symmetry breaking does more than give particles mass. It creates the world. Perfect symmetry would mean a universe of uniform energy. No structure, no variation, no chemistry, no stars, no life. Every interesting feature, galaxies, planets, molecules, biology, comes from broken symmetry. Think about what this means. We live in the wreckage of broken symmetries, and that wreckage is everything we are. Now let me tell you about the biggest symmetry problem of all, matter and antimatter. You see, every particle has an antiparticle, electron and positron, proton and antiproton, neutron and antineutron. When particle and antiparticle meet, they annihilate. All their mass converts to energy. This happens. This is not theoretical. We see it in particle accelerators. We see it in cosmic rays. Particle-antiparticle annihilation is one of the most thoroughly confirmed processes in physics. The equations of physics are almost perfectly symmetric between matter and antimatter. If you take any physical process and swap every particle for its antiparticle, flip the sign of every charge, and reverse the direction of time, this is called CPT symmetry. The process still obeys the laws of physics. Matter and antimatter are mirror images, evolving in opposite directions through time. So the Big Bang should have created equal amounts, exactly equal, for every quark an antiquark, for every electron a positron, and then they should have found each other and annihilated. The universe should be nothing but photons, radiation from the annihilation, expanding forever in the dark. But we exist. You are made of matter, not antimatter. The stars are matter. The galaxies are matter. When cosmic rays hit the atmosphere, we detect a tiny amount of antimatter positrons, antiprotons, but almost nothing compared to matter. The universe is made of matter, and nobody knows why. Well, that is not quite true. We have some ideas. There must be an asymmetry. Somewhere in the laws of physics, there must be a process that creates slightly more matter than antimatter. Physicists call this baryogenesis, the creation of baryons, the class of particles that includes protons and neutrons. For baryogenesis to work, you need three things. First, you need baryon number violation processes that can create more matter than antimatter. Second, you need C and CP violation processes that do not treat matter and antimatter identically. Third, you need the universe out of thermal equilibrium conditions, where these processes can leave a lasting imbalance. And you know what? We have found CP violation. In 1964, physicists James Cronin and Val Fitch discovered that certain particle decays, specifically decays of particles called kaons, violate CP symmetry. Matter and antimatter do not behave exactly the same. In 2001, experiments at SLAC and KEK confirmed similar CP violation in B mesons. This is real. The symmetry is broken. But here is the problem. The amount of CP violation we have measured is not enough, not even close. If you calculate how much matter-antimatter asymmetry these known processes produce, you get a universe with about 1/1000th the amount of matter we actually observe. Something else is happening. Some other source of CP violation that we have not found yet. This is one of the major unsolved problems in physics. Why does anything exist at all? Why is there something rather than nothing? The answer is hidden in symmetry breaking we do not yet understand. And this brings me to something I want you to really think about. Symmetry is the foundation of physical law. Conservation of energy, conservation of momentum, conservation of charge, all of these come from symmetries. The forces of nature, electromagnetism, weak force, strong force, all come from symmetries. The particles themselves, photons, gluons, W and Z bosons, exist because symmetries demand them. Symmetry is the deepest principle we know, yet asymmetry is the foundation of existence. The Higgs breaks electroweak symmetry, giving particles mass. Without that breaking, electrons would be massless, atoms could not form, chemistry would not exist. The cooling early universe breaks symmetries, creating distinct forces. Without that breaking, there would be no stars, no fusion, no heavy elements. Unknown processes break matter, antimatter symmetry, allowing matter to dominate. Without that breaking, the universe would be empty radiation. Every interesting thing requires broken symmetry. Perfect symmetry means perfect uniformity. No gradients, no structure, no complexity. Life is possible only because symmetries broke. We are the children of broken symmetries. Every atom in your body exists because the universe is not perfectly symmetric. You think, you feel, you wonder about these things because the laws of physics are beautiful and symmetric, but the universe they govern is messy and broken. Now, there's something very deep here that I want to make sure you understand. When physicists talk about symmetry, they do not mean the universe looks the same if you flip it around. That is spatial symmetry, and that is broken all over the place. Your left hand is not the same as your right hand. What they mean is that the laws themselves do not change under certain transformations. The laws are symmetric. The outcomes do not have to be. This is what spontaneous symmetry breaking means. The laws have a symmetry that the state of the universe does not respect. The Higgs field could have taken a value of 0 that would preserve electroweak symmetry, but it did not. It took a non-zero value, breaking the symmetry, even though the laws themselves are still symmetric. And this is very interesting because it means symmetry is hidden. The universe does not look symmetric, but the laws are. The asymmetry we see, matter without antimatter, distinct forces, massive particles, is all emergent. It comes from a symmetric foundation. That is one of the great lessons of 20th century physics. The universe is governed by beautiful symmetric laws, but the world we observe is the result of broken symmetries. Symmetry is fundamental. Asymmetry is what makes reality interesting. Let me tell you about one more symmetry that is very important: time reversal symmetry. Most of the fundamental laws of physics are time reversible. If you film a particle interaction and play it backward, it still obeys the laws of physics. Electromagnetism is time reversible. Gravity is time reversible. The strong nuclear force is time reversible. Even the weak nuclear force is almost time reversible. There are tiny violations, but they are very small. Yet the universe has a definite direction in time. Entropy increases. Eggs scramble but do not unscramble. Cups shatter but do not reassemble. You age, you do not get younger. Time has an arrow. Why? If the laws are reversible, why is the universe not? The answer is another kind of symmetry breaking. The early universe was in a very low entropy state, very ordered, very far from equilibrium. And the second law of thermodynamics says entropy increases. The universe evolves from low entropy to high entropy. That increase defines the direction of time. But why was the early universe low entropy in the first place? Nobody knows. This is one of the deepest unsolved questions in cosmology. The Big Bang started with the universe in an incredibly special, incredibly ordered state. That is a broken symmetry time reversal. Symmetry is broken by the initial conditions. And because of that breaking, time has a direction. Cause precedes effect. Memory exists. Life exists. Once again, broken symmetry makes reality possible. Now, I want you to understand how profound this is. Symmetry is not just an aesthetic principle. It is not just that physicists like beautiful equations, though we do. Symmetry is the fundamental organizing principle of the universe. Every conservation law comes from a symmetry. Every force comes from a symmetry. Every particle comes from a symmetry. If you want to understand the universe, you have to understand symmetry. But the universe you see, this messy, complicated, interesting universe with stars and planets and people, exists because symmetries broke. Perfect symmetry would be sterile. It would be uniform. It would be boring. Broken symmetry creates structure. It creates complexity. It creates us. And that, I think, is beautiful. The laws are perfect and symmetric. The universe they create is imperfect and asymmetric. We live in the gap between the two. We are made of the wreckage. And in that wreckage, somehow consciousness emerged. Somehow the universe became capable of understanding itself, of discovering Noether's theorem, of detecting the Higgs boson, of asking why there is something rather than nothing. You know, there is something Emmy Noether said that I think captures this. She was asked once why she did mathematics, why she cared about these abstract symmetries, and she said she found them beautiful, not useful, not practical, beautiful. The symmetries exist whether we discover them or not. They govern reality whether we understand them or not. But we can understand them. We can see the hidden order. We can glimpse the structure beneath the chaos. And when you do that, when you realize that conservation of energy is just time translation symmetry, that the photon exists because of gauge invariance, that you exist because matter-antimatter symmetry broke in the first fraction of a second after the Big Bang. When you understand all of that, the universe does not become smaller. It becomes larger, more strange, more wonderful. We do not know why the Higgs field has the value it does. We do not know what broke matter-antimatter symmetry. We do not know why the early universe was low entropy. These are open questions. We keep looking. That is science. That is how it works. But we do know that symmetry is the foundation of physical law, and we do know that broken symmetry is the foundation of physical reality. Those two truths, symmetry explains everything and broken symmetry creates everything, are not contradictory. They are complementary. They are both true. And together, they tell us something profound about the nature of existence. Symmetry is beautiful, but life requires asymmetry. Perfection is sterile. Imperfection is fertile. The universe is governed by perfect laws, and it creates imperfect structures, and we are one of those structures, made of stardust and broken symmetries, trying to understand how it all works. And here we are, made of that stuff, figuring this out. Think about that.